about this connection because there are the what you call the induced voltage that we can get from this kind of construction is different based on what we call the sequence of connection to the commutator segments. Okay, because activation of each of the coils are different depending on the connection. Say in the case of progressive winding, which is what we see in the lap winding just now. For progressive means like one end is connected to one commutator segment and the other end is connected immediately to the next commutator segment. So there are two different types of windings, which is either simplex or multiplex, in which the sequence of connection to commutator segments will be either lap, wave or frog leg. Okay, so multiplex means you have multiple windings on the coil. Okay, so you will have lap, wave and frog leg. Okay, so what you see here, there are few variables. Okay, C is number of coil, of course we see just now. P is number of pole. A is the what we call current path. Okay, so I think yeah, we can see from here A is the total number of current path. Okay, and to determine, so basically so to determine the current path for each of the connection, it's different depending on whether you are connected it by lap winding, a wave winding or a frog leg. Okay, for a multiplex it will depend on the number of windings that you put together. So for a simplex you just have only one, so multiplex you can probably have 2, 4, 8 or something. So you can multiply with that number, okay, which is M lah. Alright, sorry. You also have what we call a retrogressive winding, in which the first, so it's like it's connected backward. So it's like the first side of a coil is connected to one commutator, and the end of it is connected to the commutator before it. Okay, so there are two types as well, simplex and multiplex, and you can see that the current path is quite the same. Okay, alright, so the influence is here. Okay, so we know that EA, in the case of we compute it previously for a single coil, it is 2 over pi times flux times omega m, right? But now, because we have not just single coil but multiple coils, and also a different type of connection to each of the commutator, EA is basically will depend on Z, which is the number of conductor that we have seen just now, which is 2C times the number 2C times the number of turns. Okay, betul lah. Okay, so times the number of turns, right? And then you also have the velocity, okay, of the linear velocity, and the number the magnetic field density, and then the length of the conductor, and A is number of current and total number of current path, which is depends on the type of winding. Okay, so generally in this lecture, the whole information that you see here is well, important for those who are doing the machine design, but for this subject we will try to simplify, not to go through directly into how the machines are, how the windings are connected, but we will go through to see how we can simplify this equation into a more compact version of how we can determine EA. Okay, so if we replace the values, remember that we can replace the value of V into R omega, and as well as getting the what you call the pole surface area and so on, and we split them into this equation. You can split them into this equation. Alright, so if we split them into this equation, what we'll see is that this term here is actually the flux, right? Because 2 pi RL over the number of pole is actually A, right? So because this is AP, right? So 2 pi RL is the whole surface area of a rotor, of a cylindrical surface of a rotor, and then you divide by P, which is the number of poles. So A over P is actually AP. Okay, so surface area per pole. So if you have 2 poles, then you will divide 2 pi RL over 2, which is you have pi RL, which is the surface area of AP. So we calculate before this that AP times B, it is actually the total flux inside the machine. Okay, so what we left off are this term. Okay, alright, so this term is what we call the machine constant. So previously for a single coil, we have the term as 2 over pi, okay, but for a machine, for real machines, we have multiple coils and the number of conductors inside the rotor are different, and you have more than one single coil, or more than 2 conductors in one single coil. So you will have this term as a constant, which is number of conductors, number of poles, number of current path. Okay, so this will give, if we replace this term as one single value K, we can call that this as a machine constant. Okay, so the same equation can also be done like this if we replace omega into the term RPM. So N here is speed in RPM. Okay, so you will see that, oops, sorry. Okay, so you will see that the term now has added 2 pi over 60, right? Because to change from RPM to radian per second, we have to multiply with 2 pi over 60. Okay, all right. And therefore you have this term. Okay, so it is the same thing as the one you see on your left. All right, so it's the same thing, but right now we just change this term instead of omega into RPM. Okay, so if we have some speed in RPM, the term ZP inside the term K here is not ZP over 2 pi A, but it's ZP over 60A. Okay, so EA in this case is K prime phi NM. Okay, so the difference here is simply in the term K, which is machine constant in radian. If you have speed in radian per second is K. The machine constant when you have speed in RPM, you have K prime. But anyhow, we can see that the induced voltage is determined by the machine constant, the flux, total flux in the machine, as well as the speed in the motor. So in many what you call practice questions, as well as exam questions, and even in reality, they will not give you exactly how progressive winding and so on is done, but instead they will give you some kind of machine constant. So this machine constant sometimes have a value of 1.5, 2, 1.8, something like that. So it's easier to plug in. You don't have to go through the hassle of finding the total number of current path and so on based on the construction of the winding. So what you see in the lecture today is the reference of how these current paths are determined. Okay, if it is regressive or if it has a simplex or multiplex winding, you will have a different current path, and therefore you will have a different machine constant, okay, at the end, which will have a different K for different type of windings that you connect to the commutator. Okay.